Hello, good afternoon everyone. Welcome to the class ECE341, the probability and stochastic process. Okay, ECE341. This is a 13-week Monday's class. Okay, now we will start a new chapter, the last chapter, the stochastic process. Stochastic process. Okay, so what is a stochastic process? Stochastic process, you can think is a kind of a sequence of random variables. You have a lot of random variables. They have a list. They forms like a process. Actually, I say like that. We have 4 different kind of stochastic process. So, x of t. T is the time. T is the time. Run from negative to positive, infinite. X of t is a random variable. For every t. For every t, this is random variable. So this is a random process. This is stochastic process. We can also call this as a random process. Same meaning. So for every t you have a random variable. Then as a list, as a process, right? Process. Or like x of n. Now n is also a time, but this is a discrete time. N must be integers. It will be 0, positive, negative 1, positive, negative 2, and so on. And of course, it's a random thing. If they are fixed number, they are not a random process. We want is every x of n is a random variable. For every n. So if we say a random process, then we have these 2 kind of things. Both are random process. One is for continuous time, one is for discrete time. This is continuous time. Continuous time. And we know for random variables we have 2 kind of random variables, right? We can have discrete value random variable or continuous value random variable. So we also have we can have we also have discrete value or continuous value. Stochastic process. So totally we have 4 different cases. 4 cases. Continuous time and continuous value, continuous time and discrete time value, discrete value. We have discrete time and continuous value, and discrete time and discrete time value. So we have 4 different kind of random process, the stochastic process. In the real application, like in the signal processing, our ECE, usually when you study a signal, that signal is a random process. The signal usually a signal will combine with some noise, some disturbance, that is kind of random thing. So we can just think they are stochastic process. They are a sequence of random values, a sequence of random variables. Okay, we can consider some example. We consider like suppose x is a uniform distribution from A to B, and this is a uniform distribution. Then we use x1, x2 until infinite, and even some negative xn's. They are independent symbols of x. Then xn is a random process. This is a discrete time, right? Discrete time. And continuous value. Stochastic process. Right. Yeah. And another example, I use x by like a Bernoulli P. Okay, this is discrete value, right? The x could be 0 or 1, only 0 or 1, two possible values. And we let x of t equal to t plus x. Okay, then that means like you randomly take x, you get x is 1, then x of t will be t plus 1. If x is 0, you have x of t will be t plus just t, if x is 0, right? So this case, this is t, and what is x of t? It will be t if x equal to 0. X of t will be t plus 1. This is t plus 1. This is t plus 1 if x is 1. So this is, you can say this is a if you look at it overall for all the t, the result will be two straight lines or two functions. X are functions. X are functions of t, right? You have two different functions depending on the value of x. You will pick x randomly, so it will be 0 or 1. If it is 0, you have this function. If you have 1, then you have this function. And then for every t, when you look at every t, you fix a t, then you have this value and this value. These values, they are randomly, right? It is depending on capital X. Before you get value of x, these two, you cannot make sure which one will happen. And when you get the result on x, then you know, okay, the value will be either t or t plus 1. Right? So this is also random process. For every t, this is random. Every t is a random. But this time, this x of t is continuous time. Continuous time with discrete values. Yeah, this is a random process. It's a random process. Random stochastic process. Okay. This is stochastic process. It is continuous time and discrete value. I told you we have 4 different cases. You can try to find different symbols. And okay, we can still use this one, but this time, example, x is a Bernoulli P. For every t, let xt also obey Bernoulli. I say xt is a symbol of x, and when t different, if t1 do not equal t2, xt1 and xt2, they are independent. Okay, so yeah, this is also coming from that Bernoulli, but this time for every t, you can have two values. You can pick two values. Every t you have two choice. And for different t, they are independent. So that means if this value you pick 0, then you for another one it could be still, you still have two choice. So every t you can have independently. Every time you can have value either 1 or 0. Alright, and let z equal to t plus this x. Okay, this z is similar with this x, similar with previous x, right? This one, but this time, it is not straight line because this x is uncertain. So it will be, it is t plus value 0 or 1. T plus 0 or 1. It's not straight line. In this example, totally we have only, you can think only two possible values, x is 0 or x is 1. If x is 0, xt is a straight line. If x is 1, this x is also a straight line, but another straight line, right? Two lines. And here, every xt is randomly, and z is t plus x. So every t you have a zt, right? Zt equal to t plus xt. Not this. Zt equal to t plus xt. Zt equal to t plus xt. Then xt is randomly. This is also random, right? Randomly. Yeah, it's more random than that one. You can think like that. All right. So this is also continuous time and discrete value. Right? Discrete value. All right. Okay. Now we consider the distribution functions. Function of probabilities. Of a stochastic process. Now we have, similar, right? We have CDF. We have the mass function PMF. We have density function, the PDF. Right? We still have these three. And not just one. We also for different. You have a sequence, right? You can pick any variables from the process. Then you can have several random variables. So you can also have the joint one, joint and a single. Right? You can have two choice. Then you have a lot. For example, for process, x of t, you can have CDF like f x t of x. You just pick one time. Right? This one by definition we know that it's for CDF. CDF will be the probability of xt smaller than or equal to this x, right? We have this. We can also have a joint one. We have joint like a t1, xt2, or maybe more. Maybe not just the t1, t2. You can have whatever do you want, like tm. Then here's x1, x2 until xm. This one will be the probability of xt1 smaller than x1, xt2 smaller than x2, until x of tm smaller than xm. Now you can have this kind of thing. Okay, this is a CDF. You can also have the PDF if it is a continuous, if x is a continuous value. Then you can have the density function, the PDF. You can have joint x1 to xm, right? You can have PDF and joint PDF. The PDF is a joint PDF. You can take derivative from the CDF, you can get this PDF, right? And you also have the if x is discrete value. Then you have the pxt of x, or p xt1, xt2 to some xtm, then x1 to xm, like this. Alright. Okay, here I write all these use t. So this is a case for continuous time case. For discrete time case, you just replace this t by an index like n or m. Then you have the similar description for discrete time process. So I will say there's a lot. Even you just study one process, you will have a lot of this kind of functions. For every time, fixed t or fixed n, you have a CDF, PDF, PMF, and you pick some of the variables from the process. Then you can have the joint distributions. And how many joint distribution do you have? Infinite, right? You pick any 2, any 3, any 5, any 10 of the random variables, you can have a joint distribution. Okay, so I have to say, this kind of things is very complex. It's hard to study, even hard to be used. So we need to make some simplify. We need to make some simplify. Okay, then we have several things. Let me see. Okay, some special process. We give some restrictions. The first one is a IID process. IID, that means independent. The second I is identical. Identically, and the D is a distribution. Independent, identically distribution. How to say? Identity. Check. Yeah, just like this. Yeah, independent, identically distributed. process. That means xt the same with for different t they have for any t has same distribution. And they are independent of each other. And the example of these independent sample tree. Independent sample tree. Sample tree of random variable x. Now we have this a lot, right? In the statistic part, you take sample like you have x, then you take n samples, x1 to xn, x1, x2 until xn, and more. This is a kind of IID, right? This is IID. All of them, they have same distribution with x, and they are independent of each other. So this is IID process. And the second one, we say it is a stationary process. Stationary process. Stationary process, that means they have same distribution when time is different. So we have these. We have f x of t x or equal to f x of t1 x if t do not equal to t1. So this is similar with that. It's identically distributed, but they might be independent, and maybe they are dependent, not independent. Okay, and the second we want f of x t1 t x of t2. We pick any m of the random variables from the process, x1, x2, xm. That this is the CDF of these m variables from the process. They have the joint CDF. This joint CDF were equal to f of capital X of t1 plus a tau, x of t2 plus a tau, x of tm plus a tau, and here is still x1, x2 to xm. Do we have these? We have these. The second one is for any m random variables x random variables from the process. Okay, the first one you pick m, and then you use another m. This set of m's, the index, you see, just plus tau. Then they are same. Okay, for any of them, and for any tau. Okay, so this is a stationary process. You can see ID is a special case of stationary process, but the stationary process contains more process than ID, because this one can be used to some process. They are not independent of each other. They are dependent on each other. And the third case is wide sense stationary process. Wide sense stationary process. write it as WSS process. What's that? Okay, we want the min of each xt. They will be a constant. So like I suppose like all of them they equal each other, right? So they equal to the e. They equal to the t equal to 0. When t is 0, x of 0, you check the min. Then all the rest, they have same min with the 0 time variables for any t. Second one is a covariance. Covariance of x t, and let me see. I want covariance of x t and x t plus tau or equal to covariance of x0 and x0 plus tau. That's for any t and any tau. Any t and any tau. Okay, so this is also kind of a stationary. It's a y-sense stationary. Here we do not have the description with the functions, right? So like here the stationary is described by the functions. And now we just check the min and the covariance. Alright, so by this way, this kind of process we can handle it easier. We just start from the min and the covariance. We can do a lot of calculations. And for this stationary process, you have to start from all these distribution functions, CDF. You have to start from the CDF, or similar, you start from PDF or from PMF. That is more complex, right? So the second type, by definition, is very complex. How to apply them is also complex. Then we use this one. Okay. Alright, now we have the relation like this. IID process, must be a stationary. It is also must be y-sense stationary. And the stationary must be y-sense stationary. But if we go this way, no. If we go this way, no. So you can have a process, it is y-sense stationary, but it is not IID, it is not stationary. And this two, from here to here, I will say no. So if a process is a stationary, then we cannot say it must be an IID. Yeah. But if it is IID, it must be stationary. If it is IID, it must be y-sense stationary. Alright. For the basic concept of the stochastic process, I think in this class I just give you this. Alright. We will have more classes. We need a random process. We need a stochastic process. So when you go to those classes, you can learn more. Like some courses with signal processing, with communication. Yeah, you need more knowledge about the stochastic process. But here I just introduced this part to you. Alright, now we check some examples. Example. Okay, I can use the previous example, right? I have which one? Okay, I have X obey the Bernoulli. Bernoulli P, and I have X of T equal to T plus X. Now we have this one. So we can study the feature of this one, what kind of information we can have. Like the first one, we want to know the, okay, we already know this is a continuous type and discrete value, right? We already know this. Yeah. Now we want to find the distribution of it. We want to find the distribution of it. This is a discrete time, so we want the PMF of xt. Can we have these? Okay, so this one is a P of x of t of x. This is the probability of, I just use P, if I just PR, okay, I use PR for the probability of xt equal to x. So this is a probability of, what is xt? It is t plus x. This equal to x. So we have px of t of x equal to, this is a probability of, now it is x equal to lowercase x minus t. It's this one. Okay, then this one we know, because this is a Bernoulli distribution, so it has 3 possible values. It will be p, or be 1 minus p, or be 0. This case is x minus t equal to 1, right? If this is 1, then the probability will be p. If this is 0, the probability will be this one, and all the other values. Otherwise, the probability is 0. Okay, now the function is on x, right? On x, so I need to write this in terms of x. So it is this is a p. Now it's x equal to 1 plus t, right? And it is 1 minus p. Here x, if x is t, and otherwise. Okay, we have the PMF. We have PMF. It looks like this is x. This is a px of t of x. It will be at t, time t, and 1 plus t. Then we have probability 1 is p, lowercase p, 1 is 1 minus lowercase p, things like that. And x, you know, for x, this is px, and px of x, it will be 0 and sorry, I put the wrong one. T is 1 minus p, and t is 1 plus p. Here should be p. It should be p. Okay, so this will be p and 1 minus p. This is also p and 1 minus p, and shifted by t. Here's t equal to 0. Here's x equal to 0. Here's x equal to t. X equal to t. And the t is different, right? T is time. For different time, this one, the waveform is same. The function's form looks the same, but the location is different. Right? Shifted. For larger t, these two peaks will go to right. For smaller t, these two values will go to right, go to left, right? Okay, this is the distribution, the function. And second one, we want to find the we know it is we have the concept the ID, the stationary or y sense. So this one won't be anything. It is ID. No, because for different t, the distribution is different, right? The location is different. When t is changed, this one will change, right? This is a t equal to 0. X of 0 is also this one, but x of some different t, you see they are same? They are different, right? They are different. So we say x of t, it is not IID, right? Different t, they are different. Different t gives different px t of x. So for ID, they must be same and independent. So here they are not same. And the third one, no, they are not, I have several things. I1, and third one, are they the stationary? Still not, right? Still not. We say stationary, then for different time they should have the same distribution, and when you consider joint distribution, they have this relation. But now it is not. Now it is not. So it is not stationary. Not stationary. And the third one, of course, it is not Y-sense stationary, because the mean is also different, right? The mean will be a value, some value here. Here mean will be here. When you are moving for different t, the mean is changing. The variance will be same, but the mean is changing. And the covariance, yeah, they are related, right? They are coming from same x. So if you check the covariance, there should be some value where not to be a fixed value. Right? So none of them. And of course we want to calculate those values. We want to find those average values. Average values. We consider the E of x of t. Okay, here we can use the notation. We can use the notation mu x of t. We use mu to replace this x of E of x of t. Is this shorter? Yeah, somehow it looks shorter, right? So we use this. You can use this notation for this one. Okay, then we use the definition. What is the expectation value? This is discrete type, so we need to do summation. All the possible x. Here's x times the mass function, property mass function. Right. And we know the mass function is here. Its value, when x equal to these two values, we have these two probabilities. So it is x is 1 plus t with probability p, and when x is t with probability 1 minus p. Okay, and all the rest the probability are zeros, so we only need two terms. Then this is p plus tp plus t minus tp. So these two cancel. So it's p plus t. P plus t. This is the average. And then we calculated the variance. Variance of x of t. Actually, we denoted as sigma square x of t. We denote by this one. Yeah, here you can think it's square. It is also a part of the whole notation. This is a notation of the variance. If you remove this, there will be standard deviation. Okay, then this one, it will be E of xt squared minus ex of t squared, the outside square. Right. Then this will be similar. We do the summation, but now I need a square. So x squared and the px of t, x for Rx, and the plus and the minus the square of this is p plus t squared. Right. And what it is, we only have two values, right? We have two non-zero probabilities. So this is x is 1 plus t, now is a square, times the probability p, and x is just t squared times the probability, and minus this one, p plus t squared. Okay, let me do the calculation. I need to separate them. This is 1 times p plus 2t times p, and the t squared times p. Second term is t squared minus t squared p, and the last one is minus p squared minus 2pt minus t squared. okay, we should have some term to be cancelled, right? Can we? Yeah, t squared and t squared, they cancel, right? And negative 2pt, positive 2tp, they cancel. Anymore? These two. T squared p, positive, negative. So this is a p minus p squared. You can also write as p times 1 minus p. This is the variance. Variance of this random process for different t. Okay, this number is independent with t, but this one is dependent, right? Contained with some t inside. And we can also have the variance, covariance. The covariance of x of t and x of t plus a tau for different t. If tau is 0, they should be same. When tau is not 0, these two different random variables, and we check the covariance. And this will be e of x of t times x of t plus tau minus e of xt times e of x of t plus tau. Right? We have this one. Actually, we have name. We call this. We have this notation. This is just a c, x, t, and the tau. Yeah, this notation shorter, right? This COV, you just put c. Then you have 2x here, then just 1x. Then for time, you put the t and the tau. So this one denote this one. Alright, so we use this notation. Alright, then the probability. Okay, here's you need to time these two together. Okay, so both are x. Yeah, this one, the first one is t. I have x is a t. What? T plus. What is x? I forget. Is x minus t. Huh? X is what? Sorry. Which page? Which papers? I have. It's here. X is t plus x. T plus x. Right? X is t plus x. So this one is t plus x times. This is a t plus tau plus x, right? And minus this one we calculated e of x is a p plus t, right? P plus t. So this one is a p plus t, times this will be p plus a different t, different t, right? It's a t plus tau now. Yeah. Okay, so this one will equal to e of there's a lot. Let me times them together. So t times all of these, I get t squared plus t tau plus tx. Then x times them plus xt plus x tau plus x squared minus this part, p plus t and p plus t plus tau. Alright, what it is. Okay, now t squared and t tau and the t and the tau, they are not random value. They are just time, right? They give they are times. For different time, they are different, but they are not random value. So you take expectation, they are just the same value. And this one is t times ex, right? And this is this is also t times ex. So these two I can merge together, two of it. And plus this is a tau times ex. Right? This is tau times ex and e of x squared. and minus p plus t and p plus t plus tau. Alright, what was your lot? Let me step by step. T squared copied. T times tau, this is 1. And ex is x is the original process, right? The original random variable, the Bernoulli p. So this is p. So plus 2t times p. And this is tau times p. And the ex squared. What is ex squared? And you remember for Bernoulli, it's a p squared. It is p squared. It is p squared, I think. It's a p or p squared. It's a p. Ex squared is also p. Right? X squared will have value 0 and 1. And the probability will be p and 1 minus p. Then you take average 1 times p, 0 times this, just 1 times p. Yeah, it is p. And minus, okay, this part it is p squared plus pt plus p tau, and time plus tp plus t squared plus t tau plus t tau. Alright, then can we cancel something? I have t squared here. This t squared can be cancelled, right? I have tau p. This tau p, they cancel. I have t tau. Both contain t tau, they cancel. Anything else? Here's a p. Here's also a p, they cancel. Okay. Alright, this is a 2tp minus p squared minus pt, right? Minus p squared minus pt. I think why this cancel this tp? No, sorry. Let's do it again. I think I did something wrong. This t squared and this t squared, they cancel, right? Then I have t tau. This t tau, they cancel. Then I have 2tp. Yeah, that's a problem. I have 2tp. At 2tp, here's a pt, here's another tp, and here's a 2tp. They cancel. Yeah, they cancel. Then top p and top p, they cancel. Okay, finally we only have p minus p squared. Covariance. Okay, so the covariance is always a constant, no matter what is the t and pp. Am I good? I doubt. Yeah, check it with me. Am I good? If tau is okay, yeah, they are same. So it doesn't matter what is the covariance is always this one. Okay, so it is this one. Alright, it's always this one. I think it's good. I think it's good. Okay, so this is an example. The covariance is always equal to this one for different t and different tau. Right? Different t and different tau. Okay, so yeah, what else I want to get? Actually, we have another one. We have the correlation, right? Correlation, r of x t and x of t plus tau, which is defined as the expectation value of xt times x of t plus tau. And this one is denoted as r, x, t, and tau. We use this notation for this one. And it will be this, and you need to do some calculation. Actually, it is this one, right? It is this one. So it is just this part. It is part. Okay, so this time it will be this time, this part. So this one is more complex than the covariance. This will be, I just copy it, t squared plus t tau plus 2tp plus tau p plus p. Do I have square here? No. The square is that one. Square. Only just p. Okay, it is this one. What it is? Anyway, this is a complex one, but it's a function, right? Depending on the t and the tau. for different t, different tau, this one is different. And we have relation looks like this. Alright. Okay, that's all for today. See you next time. Bye.